Everyone can see the slide? You can hear my voice and you can see the slide. Please let me know. Okay, very good. Okay, just now we said in order to get the influence line, our main target is to move the load over the span and then see into the change in the reaction. So we just saw that how we can get the influence line for support reaction at point A and how we can get the influence line for support reaction at point B. What we did, we just moved the load from left to right. We calculated how much is the value of RA at any specific location that the load is going to be there. And we saw that for RA, when the load is moving from point A to point B, basically the value of RA is going to change from 1 to 0. And vice versa, we did the same calculation for point B. We saw that the value is going to change from 0 to 1. So this changes is the value of the support reaction as the load passed from A to point B. So it was very easy to do this calculation for support reaction at point A and point B. We just change the location of the load and calculate how much is RA. The graph that shows the value of RA as the load change is giving us the support reaction. We can do the same calculation, but this time we want to see the influence line for shear force. So this too was influence line for support reaction because they were looking into the value of support reaction as the force was moving from one side to another side. Now let's go and see how is going to be our calculation when it comes to shear force. So the same beam that just now we analyzed the influence line of support reactions are going to be taken into account to get the support shear force influence line. So this is our beam. We have put two locations, point A and point B, or point 1 and point 2. So we want to see how the shear force at point 1 and point 2 is going to change when the load is passing from point A to point B. So this is our target right now. So the shear force at point A is the first target. As I said, one by one, we need to do the calculation. First, we are going to look into the shear force diagram. A shear force influence line at point A. And then after we calculate that one, we will look into the shear force influence line at point 2. Okay, it is just a reminder here that what are the positive and negative signs for shear force. So if you cut your beam from point 1, you look into the left side, toward down considered to be a positive sign, and toward up in the right side considered to be positive sign. So right now, similar to what we did for support reactions. First, we are going to assume the support the force is in the beginning, and then it moves, reach to point 1, and then after that it can pass point 1 and reach to point B. And for each location, we are going to see how is going to be the value of shear force at point 1. So this is what we have done here. Since our interest is point 1, we look into the point 1 when the force, that moving load, is between point A and point 1, which is this area. And the second case is when point 1, the moving load is already past point 1, which is going to be this case. So when the moving load, is between point A and point 1, we have this condition. And when the moving load has passed point 1, we have this condition. For these two, we are going to get two different equations for the value of shear force. Okay, let's look into the first condition or first case. When the moving load still hasn't reached to point 1, and we have this condition in our beam, you can easily cut your beam from point 1, look into the shear force, and then you can write down sigma Fy equals to 0. And from there, you can see that the shear force that you add it, or you want to calculate it, regardless where is the location of basically load, equals to negative value of R in the right side. So in other words, when the point load is moving from point A to point 1, the value of the shear force at this location is always negatively equals to R at the support reaction at point B. That here we have referred to it as RR, right side, or RB, doesn't matter. However, when the load has passed point 1, this location, then if you cut your beam from the same location, point 1, then you can look into the left side and you can see the moment that the load passed point 1, always your shear force equals to support reaction in the left side of your beam. Sigma of y equals to 0, V is going to equal to RL or RA, doesn't matter how you're going to refer to it. So we have two cases. One case is when the moving load hasn't reached 2.1, and the second case is the load has passed point 1. If the load is between point A and point 1, we can always say that our shear force equals to the support reaction in the left side, but with negative sign, because we can write down sigma of y equals to 0. So this shear force equals to this one, right? On the other side, when the load passed point 1, okay, then we can again cut our beam from point 1, and we can see that our shear force is equal to the support reaction in the left side. So if we have the value, or better to say the influence line for support reaction in the left side and right side, we can easily get the influence line of shear force based on these two. Because this calculation just now we made says to us that when the load is before point 1, shear force influence line is similar to the support reaction influence line in the left side, but with negative sign. When the load passed point 1, the influence line of shear force at point 1 equals to influence line at point A, support reaction at point A. So if we have already calculated the influence line for point A and point B, or left and right side, we can easily get the value of, or better to say, the influence line of shear force at point 1 based on them. If you go back to our calculation, so we can see we have already have the influence line for RA and RB. According to our calculation, when the load is between A and 1, our shear force equals to the value of influence line in the left side, but with negative sign. So from point A to point 1, meaning this area, our shear force influence line should equal to the support reactions influence line, but with negative sign. So it should be similar to this, but going down. And then when you go basically to the right side of point 1, the shear force influence line equals to the right side support reaction. And the right side support reaction is similar to this one. So you can see we are going to have exactly whatever we got for RL from point 1 until point B. So from this point until end of the diagram, end of the beam, our shear force influence line is going to look like exactly this one. So if you combine these two, then this is the curve that you can get. This is the curve that we can get for shear force influence line. The beginning is exactly the one that we got for support reaction, but with negative sign. And then when we pass point 1, is going to be exactly similar to the support reaction to the left side, and with positive sign, which is going to be similar to this. So if you combine these two, you get the basically shear force influence line. Don't forget that at point 1, the value of shear force should be exactly 1. Because when the load is standing exactly at point 1, the shear force should be equal to the value of the point load. So 0.8 plus 0.2 gives us 1. That shows our calculation is correct. So you can do the same calculation for point 2. Point 2 is a point which is basically 2.4 meter before point B. So again, you can assume that the force is between A and 2, and again, the force is between 2 and B. When the force is between point A and 2, we can look into the right side of the diagram, and your shear force is going to equal to point B's support reaction with negative sign. When the load moves to between 2 and B, then your shear force equals to the support reaction at point A. So again, based on support reactions influence line at point A and at point B, you can easily calculate what is going to be the shear force influence line at point 2. So what this diagram basically are telling us is that if you're interested to know how much is the shear force at point 1 when the load passed from point A to B, you need to look into this diagram. In the beginning, when the load is here, basically, you don't have any shear force at point 1. Don't forget, we are talking about point 1. When the load is here, no shear force at point 1. However, when the load starts moving, coming to the right side, little by little, shear force at point 1 is increasing until the maximum that occurs when the load stands on point 1. The moment it passes point 1, again, it starts decreasing until it reaches to point B. Shear force at point 1 becomes 0. Similarly, for point 2, we can see the same condition, meaning when the load is in the beginning of the span, the shear force at this location is 0. However, when the load starts moving to the right side, shear force at this location becomes larger and larger. The maximum, which is 1, occurs when the load is exactly at point 2. And again start decreasing when the load reaches to point B and becomes 0. So this diagram here is influence line for shear force at point 2. This one is the influence line at shear force at point 1. So you can see, again, we are calculating the influence line not for the whole span. It is based on the interest of, based on the location of interest. In the first diagram, we wanted to see the shear force influence line at point 1. In the second diagram, we wanted to see the shear force diagram at point 2. So you can see these two are not similar, and it has to be the same because you're looking into two different locations. Each one of them is giving us a different diagram for the shear force when the load is moving from point A to B. Of course, you may draw another shear force influence line for the middle of the span. In that case, the diagram is going to look like similar to these other two, but the maximum is going to occur right in the middle of the span, negative 0.1 and positive 0.5. Is going to be a symmetric diagram, one side negative, one side positive. So it is up to you to see which location is important for you when you want to design your beam. But of course, you need to find the most critical location. Sometimes we draw for several locations, and then we will look into the maximum of those locations. Anyhow, so what we observe basically from this calculation is that you can always calculate the shear force influence line based on what you have obtained for the support reaction. This is why normally we get the influence line for supports first, and then based on the supports, we can easily calculate the shear influence line or bending moment influence line for any other locations that you are looking for. And now that we got this one for shear force, we can do the same calculation, this time for bending moment, meaning we are interested to see the influence line for bending moment at point 1 and point 2. Our calculation is going to be exactly similar to what we did for shear force, meaning once we assume that the load is before point 1, and then after that we can assume that the load has passed point 1. When the load is before point 1, we get one equation for bending moment here. When the load passes point 1, again we get another equation for the bending moment at point 1. And these two equations is going to define the shape of bending moment influence line. Let's go and see how we can do that. Okay, now first we are going to draw the influence line for bending moment at point 1. So we are interested to point 1 right now. If the load is before point 1, okay, let's say load is any location from 0 to 1.2 meter. Okay, you cut your beam from here. Okay, you cut your beam from here. Then you can see that you have a unit load applied to this location, and then we have nothing in the other side, right side. So if you cut your beam from here, you can see that the bending moment in the point 1 equals to support reaction multiplied by this span. So regardless, where is the location of your, basically, let me draw this one, this way you can understand it better. Okay, when the load is here, any location between the point A and also the point 1, you cut your beam from here, then you can see that the bending moment that you have, this is support reaction at point B or RB. You can also refer to it as RL, for example, doesn't matter. So you have a bending moment here, Okay, you have the bending moment, and there is no load here because the load is already between A and A. It hasn't reached to point 1. So your bending moment always equals to this RB multiplied by the length of the span because you don't have any force between point A and point B. When the load passes point 1 and comes to this side, then you can look into basically point A and say that my bending moment is always equals to this RA multiplied by 1.2. So two conditions. When is the load between point A and 1, you can look into the right side of the diagram. When the load passes point 1, you can look into the left side of the diagram. And for both of the case, you can get M based on RB, because M is RB multiplied by this length. And here also M is RA multiplied by this length. So if you have the influence line for RA and RB, you just need to multiply it to the values here 4.8 and here for this diagram 1.2 to get the value of M. So it is important for us to know that we can always calculate again the influence line of bending moment based on the influence line of support reactions by just cutting the beam from the location of interest and looking to the right side or left side. Normally when we cut, we look to the side that doesn't have the load. So if I cut from here, right side doesn't have any load on it. So I can easily say that M equals to RB multiplied by 4.8. When the load goes to the right side of 0.8, meaning it's moving to this side, so I can always calculate the value of M based on RA, because RA multiplied by 1.2 is going to give me the value of bending moment. Okay, so this is what we have done here in the calculation. You can see in one case RA equals to RL multiplied by 1.2, and another one RA multiplied by 4.8, which is the length of the span. So if you do this calculation, you can get this bending moment influence line. So for point 1, we have RA, we know how much is RA. We just multiply those values to 1.2 and 4.8, and then we can get the values of bending moment, which is going to look like this one. So this curve basically is not a bending moment diagram. It's the influence line for bending moment at point 1. What does it mean? It means that when your load is moving from point A to point B, bending moment at point 1 at this location is going to change according to this diagram. When the load is here, bending moment at point 1 is 0. When the load comes to point 1, bending moment is the maximum value, 0.96. When the load moves to point B, bending moment decreases and reaches to 0. So this is the bending moment values at point 1 when the load passes from point A to point B. If you want to draw for point 2, which is a little bit after point 1, again, you can do the same calculation, meaning you can divide your beam into two pieces when the load is before point 2, when the load is after point 2. Then you get the bending moment based on RA when it is before point 2. Again, you get bending moment based on RB when the bending moment is before point 2. And you can get, again, the value of bending moment for point 2. So this diagram also is telling me that at point 2, when the load is coming from A to B, is moving. Maximum is when the load is exactly at point 2. And when the load is point A or is located at point B, bending moment is 0. And the change in the bending moment follows this curve. It increases from point A to point 2, and then decreases from point 2 to 0. So this is basically the influence line for bending moment. If you have any question until now, please ask. I'm going to explain again in the next example how we can draw the influence line for a beam, which is a little bit more complicated. This beam that just now we did the calculation was a simply supported beam, and it was very easy to do this calculation because it has only one element. And don't forget, until now, whatever we have done is for a determinate beam. And always, in a determinate beam, our influence line are changing linearly. We don't have any curvy shape when it is a determinate structure. Regardless, you are drawing influence line for bending moment, regardless you are drawing bending moment influence line for shear force or support reaction. always you have a linear increase or linear decrease. The line is linear, we don't have curve. But if you have an indeterminate structure, then you don't have linear basically changes. It follows a non-linear curve, which will be explained later on. So our basically calculation is so far for determinate structure, and the curve that we have obtained are always a linear curve. For shear force, influence line, bending moment influence line, and support reactions influence line. And what we did, we just divide our element into different small segments. We calculated the support reaction at different location. We calculated the bending moment at different location. We calculated the shear force at different location, and we draw the influence line based on the values that we have obtained. Okay, any questions so far? Any question? If you didn't understand what we did, please let me know. Any question? Is it clear what we did? Anyone else? Any question? Okay, I assume that so far there is no question. Okay, now let's make our job a little bit more difficult and look into a beam that is not a simply supported beam. So the beam that we want to investigate this time is the one that you see on the screen right now. So the beam has one roller support at point A, one hinge at point C, internal hinge, and then we have also one fixed support at point B, okay? And our intention here is to draw the influence line for many items that includes support reaction at point A, shear force at point D, bending moment at point D, shear force at point A, and bending moment at point E. But that's the last. So this is what we want to do. Okay, so we want to draw influence line for all of these parameters. Okay, let's start with RA, support reaction. So we want to know that if a unit load is passing from point A to point B, how the support reaction here is changing. This is the meaning of influence line. We want to know if a unit load is passing from point A to point B, how the support reactions value at point A are going to change. Okay, so in order to do that, basically you should know when you have hinge inside your structure, or if you have a support inside your structure, the value of influence line is going to have a change. This is why this location are considered to be a very important location in the calculation of influence line. Just now you saw that when we wanted to draw the influence line for the simply supported beam at point 1 and point 2, we said we assume that the load is before point 1, and then we assume the load is after point 1, or before point 2 and after point 2. Then we calculated the bending moments equation, and then we got the basically influence line. So when you have hinge, always before hinge and after hinge is the location that your influence line is going to have a significant change in the slope or in its value. So this location considered to be a critical location. Therefore, when you want to calculate the influence line, you may assume that always the load is before this location and then after the hinge. Then you can see the changes. Right now, we do the same. So if your load is before point C, which is a hinge here, okay? Then if you cut your beam from point C, you're going to see you have a free body diagram similar to the one that you see here. So we don't know how much is the distance between this load and support. It can be anyone. X can be 0, meaning the load can be at point A, or X can be equal to 2A, which means the load is reaching to point C. So for a location that we call it X, which is any location between A and C, we can draw the free body diagram similar to what we can see. Okay. Right now, my intention is to know how much is RA, when the load is passing from point A to C. And then after that, I will look into the condition when the load passes from point C to P. So the first case, when the load is between A and C, is this free body diagram that we see here. If I want to calculate RA, basically, I can easily write down sigma m at point C should be equal to 0. That means RA multiplied by 2A, which is the distance between point A and C, should equals to 1 multiplied by 2A minus x. Why x? Because we don't know where is the location of this point. It can be any place. So 1 is the intensity of our load, and 2A is the distance between these 2 points, and x is the location of the load. So RA multiplied by 2A should equals to 1 multiplied by 2A minus x. So from there, you can easily calculate RA. RA equals to 1 minus x over 2A. Okay, so you can just divide by 2A. This point will just goes and become this. So you can see from point A to C, this equation basically, which was calculated based on this free body diagram, represent the value of RA. So if x is 0, RA equals to 1, meaning if the load is exactly at point A, the value of RA is 1. When x equals to 2A, meaning load has moved to point C, if you put 2A here, RA becomes 0 because 1 minus 2A divided by 2A becomes 0. So that means support reaction becomes 0 when the load comes to point C. Therefore, from point A to point C, we can define the shape of an influence line for support reaction by this equation. What happens when the load passes point C? If the load passes point C, okay, again, you can cut your basically influence line from points, your beam from point C, and then again, you can look into the left side. So the difference is that you don't have this load anymore because load has passed this point and is somewhere around here, right? So in that case, if you don't have this load, you can see RA basically is going to be 0 because if you write down sigma m at point C equals to 0, RA multiplied by 2A should be 0. Therefore, RA becomes 0, meaning when the load is passing point C and reaching to point B, there is no support reaction at point A, according to our calculation. Okay, so if I want to draw the free body diagram for you to understand it better, so this case that you see here is when the location of load is between A to C. From A to C, this is our free body diagram. It can be any location between A and C. Okay. However, when the load passes point C, this is our hinge, this is our support, and this is RA. Okay. RA, and load is somewhere around here. So if load is not in the span of A to C, from A to C, then you can say that sigma m at point C equals to 0. So RA multiplied by this distance should be 0. From there, you can see RA is going to be 0. So when load passes point C, R is always 0. That's why our diagram is going to look like this one. Meaning after we pass point C, there is no shear force, and there is no support reaction at point A, according to this diagram. But before that, when the load is before point C, the shear force, the axial, the support reaction can be calculated according to this equation that we have. So this is going to be the influence line for RA. When the load is at point A, RA is 1. When the load is at point C, RA is 0. And after that also RA is 0. Okay, so this one was calculated not with any too much difficulties. Now let's go and draw the second influence line, which is influence line for shear force at point D. So we want to see how the shear force at point D changes when the load passes from point A to point B. Okay, we do the same, meaning we are going to look into point D when the load is before point D and when the load is after point D. Okay, so I cut my beam from point D. When the load is before point D, this is going to be the free body diagram. The load can be in any place between 0, beginning of the bridge, and point D. So I assume to be a distance of x. So I'm interested to know how much is this VD, the shear force at point D when the load is moving. So if you look at this free body diagram and you write down sigma of y equals to 0, that means RA minus 1 minus VD should be 0. Or in other words, VD is going to equal to RA minus 1. So if you have the influence line of RA and reduce it from from 1, you can get VD. So this is valid only when the load is moving from A to D. So our influence line for RA is given here, right? This is our influence line. At point D, RA is, you can put basically x equals to A, RA is 0.5 at this location. So if I want to use my equation to calculate VD, so in the beginning, RA is 1. So 1 minus 1 becomes 0. So you put 0 for VD. At point D, how much is RA? Is 0.5. So 0.5 minus 1 become negative 0.5. So it becomes negative 0.5. So I got portion of our influence line based on the value of RA. Based on value of RA. Now I can look into the condition when the load passes point D. When the load passes point D, this is going to be the free body diagram. So if you want to look into the value of VD, when the load is passing point D, you have no any force between A and D. So VD is going to be exactly similar to RA. If you write down sigma of y equals to 0, since you don't have any force, VD and RA are the same. Therefore, whatever is RA is going to be used for VD. So you can see our RA here is 0.5. So we put here 0.5 and then comes to 0, and after that 0. So this is going to be the influence line of VD. From A to D, it was 1 RA minus 1, which is this one, this line. And from D until the B, it's exactly RA, which is this curve. And then you connect them to each other. Of course, again, you can see at point D, we have a total of 1 because the force when it is at point D, the shear force should be exactly the same value. So negative point plus positive 0.5 together become 1. So this is going to be our influence line for shear force at point D. According to this diagram, when the load is at point 1, the shear force is 0. The maximum is when the load is at point D, and it decreases to 0 again when the force passes point D. And we don't have any shear force at point D when the load is between C and E or E and B. Okay, so this one also was for BD, and now we want to calculate influence line for MD, shear for bending moment at point D. We want to see when the load is moving from point A to B, how bending moment at point D is changing. Bending moment at point D. Okay, again, I can consider two cases. When the load is before point D, when the load is after point D. So this is the free body diagram for that cases. When the load is before point D, we have a unit force with distance of x. And this x can be any value. And the free body diagram is going to look like this one. So I am interested to know how m is changing with the location of this force. I can write down sigma m at point D should be 0. So it's going to be RA multiplied by A minus 1 multiplied by A minus x minus m equals to 0. So you can write down the equation. If you simplify the equation, finally you get this equation. That means m equals to RA multiplied by A minus x multiplied by 1. Which at the end, basically you need to put the value of the x and RA to get m. So again, you can see m depends on RA. If you got RA, you can easily get m. For example, when the load is in the beginning, meaning x is 0, our basically bending moment is going to be RA multiplied by A, which is in the beginning RA is 1, 1 multiplied by A minus x is 0. So 1 is A minus A, which is 0, multiplied by 1, which is 0. So it becomes 0. At point D, which is still valid, this equation, x equals to A, because we reached to point D. So A minus A is 0. And then we have only RA multiplied by A. So RA multiplied by A is the value that we have here, 0.58. This is the value that we get. And so this equation is valid from A to D. When the load passes point D, basically our equation changes to this one. So in this case, we don't have any load on the span between A and D. And if you write down sigma m equals to 0, we can just get that m equals to RA multiplied by A, because the force is not there anymore. So you get RA multiplied by A. And whatever is RA after point D, multiplied by A become M. So at this location, again, you can see we have the same value. At point C, RA is 0. So M becomes 0. At point E, 0. P, RA is 0. So the curve is going to follow the shape of RA. So this is going to be our bending moment influence line at point D. At point D. So that means when the load passes from A to B, M at point D is 0 when the load is here. M at point D is 0 when it reaches to C and E or B. But M become maximum when the load is exactly at point D, and it equals to A over 2. Okay, now let's just go and make it a little bit more complicated. Now this time we want to see the case of VE, influence line for shear force at point E, this location, how it's going to be. Okay, again, like before, we need to see the condition before point E and after point E. So this is what you can see here. If the load is before point E, this is the free body diagram. If the load is after point E, this is the free body diagram. Okay, so for before point E, if you want to calculate VE, we can write down sigma of y equals to 0. VE plus 1 minus RA should be 0. From there, VE is RA minus 1. So meaning, from point A to E, when the load is moving, the value of VE changes with this equation. And since we know RA, we just need to deduce it from 1 and put it there as the value of VE. So here, RA is 0. So 1 minus, RA is 1. 1 minus 1, it becomes 0. At point D is 0.5. So 0.5 minus 5, negative 0.5. At point C, RA is 0. So 0 minus 1 become negative 1. At point E, RA is 0, again negative 1. And then when the load passes point E, basically, again, we can see that we don't have this load. So you can write down sigma of y equals to 0. VE equals to RA. Since RA is 0, VE also is 0. That's why we don't have anything here. So again, you can see all of our calculations so far is based on RA, meaning the moment that we got RA, the VD, MD, and VE can be calculated based on RA. Either they are multiplication of RA or multiplication plus minus 1 or whatever values it is there. And for ME, which is the bending moment at point E, again, we can draw the same free body diagram. If the load is before point E, if the load is after point E. So this is the condition that you can see. When the load is before point E, we have this RA multiplied by 3A minus 1, 3A minus X equals to ME. So again, we can calculate ME based on RA. After that, you don't have this load, and you just say that RA multiplied by 3A equals to ME, and you can get this one. So again, based on the value that whatever has RA, you can put the value inside the equations that you have got, and you can draw the basically influence line for ME. Again, if we look at this curve is telling you that the bending moment at point E is changing according to this graph when the load is moving from point A to point B. Meaning when the load is here, ME, bending moment at this location is 0. However, bending moment at point E become maximum when the load is at point C. Meaning when the force is coming at point C at the hinge, we have a largest bending moment at point E. And then when the load comes to point E, bending moment at point E become 0. If it passes point E, again, bending moment at point E is 0. So if you want to basically design the beam for the bending moment, the worst case is when the load is at point C, if you want to know how much is bending moment here. So you can see this basically influence line are providing a very useful information for our design. So far, in our calculations, we have assumed that that moving load has intensity of 1. This is just for the sake of simplification, meaning later we will see that if the value is 10 or 100 or 200, 300, doesn't matter. The moment that you get the influence line for unit load with the intensity of 1, you can use it in order to calculate the support reaction, bending moment, and shear force for any type of load that you have applied to your structure. It can be 1, it can be 2, it can be 10, doesn't matter. This is something that we are going to look into it in our next class. Until now, what we did was to know how we can draw influence line for support reaction, influence line for shear force, influence line for bending moment. And according to whatever we saw, the moment that we get influence line for support reactions, then we can calculate the influence line of shear force and bending moment based on them by just looking into before and after the point of interest and drawing the free body diagram and calculating the shear force and bending moment based on the support reaction. So you need to calculate support reactions influence line, and then you can calculate other parameters, whatever it is shear force or bending moment influence line based on them. Okay, if you have any question, please ask regarding whatever we did so far. Otherwise, we can check on the presence of a student, and later we can see each other in next week to continue with the influence line. Any question? Was it clear everything we explained so far? Any question? Is it clear? Are you sure? Okay, so if you think that it is clear, let me ask one question. Who is ready to answer the question? Anyone is volunteer? Or I call the name? Anyone volunteer? Okay, I have a question here. You try to think about it. My question is about the influence line at point C. Influence line at point C. I want to know how does it look like if we want to draw bending moment influence line at point C. Bending moment influence line at point C. So I give you 2 minutes to think about it. Then I will ask one of you to answer the question. Our interest is to calculate bending moment influence line at point C. So how does it look like? Bending moment influence line at point C. How does it look like? Okay, your 2 minutes is finished. And if there is any volunteer can answer the question and save the others, or if there is no any volunteer, I will select the first victim. Any volunteer? Anyone is volunteer to answer. How does it look like the influence line at point C for bending moment? Anyone is volunteer? No volunteer. Okay. So let me just roll the list down and see who is going to be the first victim. Mohammed Nasser, are you in the class or only your name is here? Do you hear me, Mohammed Nasser? I can't hear you. Please speak loudly. Turn on your mic, then make sure that your speaker, your mic is on also. I cannot hear you. Do you hear me? If you hear me, please type inside the chat box. Okay, you cannot, I cannot hear you. My question is, what is the shape of influence line for point C? Bending moment at point C. If you cannot talk, you can type. We are waiting for your type. At C will be max, huh? Okay. So that shows that you haven't learned so far. Next victim. Next victim. Okay, Nura Fortuna. Naura Fortuna. Fortuna. Naura Fortuna.
Yes, Doctor.
Okay. Alhamdulillah, one person at least I can hear. Okay, how does it look like the influence line for bending moment at point C?
It will be at 0.
At 0, meaning it's going to be 0 at point C?
Yes.
How about point A, point D, point E, and point B? If we draw the influence line for bending moment at point C, how are the values at other locations, point A, D, E, and B? When the load is at point A, how much is bending moment at point C? How much is bending moment at point D? What do you think about it?
Point A will be have the highest value, I think, Doctor.
Point A will be highest when the bending moment is calculated at point C. Meaning if the load is at point A, the bending moment at point C is maximum. That's what you said?
No. If the point is calculated from A, the C will be minimum.
Okay, thank you. Now, next person. NG Yao Sheng. Are you in the class? NG Yao Sheng. Do you hear me? I cannot hear your voice. Still, I can't. So you just type if we cannot hear you. You tell me. Oh, okay, now we can hear you. What do you think about the bending moment influence line at point C? Where is the maximum of bending moment when the move passed from A to B? We can't hear you. We can hear type. Just type, please. We cannot hear you. Everyone has mic problem when it comes to question. Okay, type. You don't need to talk. You can just type. The question is, we don't hear you. Don't try to talk. You just type. My question is here, when we want to draw the influence line for bending moment at point C, where is the maximum, where is the location that gives us the maximum bending moment? Okay, you also couldn't answer it. Let's go to next one. Point D, wrong. Okay, how about seat 1 yin? Seat 1 yin. What do you think? Your mic is functioning or is having problem like others?
My mic is functioning.
Okay, good. So I want to know if you want to draw the influence line for bending moment at point C, where is the location that gives us the maximum bending moment?
I think it's at C.
C. And how much is the value? Approximate.
Approximate.
I have no idea.
Sorry, doctor, this my.
Okay, no problem. Thank you. Okay, let's go to another one. Lim Kyung Z, if I pronounce it correctly. Lim Kyung Z.
Yes, doctor.
What do you think?
I think the maximum is at C. Then the shape is like inverted perpendicular triangle. I'm not sure.
Okay, good. At least you said something, no problem. Actually, all of you answered it wrongly. Only, I think, the second student, she said something about 0, which was correct. Point C is a hinge. So regardless where is the location of load, the bending moment is always 0. When you have internal hinge, you don't have any bending moment there. So if load point is at point A, point D, point C, point E, point B, you don't have any bending moment at point C. So the influence line is going to be only a 0 line for point C. You got it? Everyone, you understood or not? Or I should ask you again. Lim Zhongyi Z, Lim Kyung Z. Did you got the point? Okay. So if you have internal hinge and you want to draw the bending moment influence line, not shear force. Shear force is going to be different. There is going to be shear at point C, shear force, but there is no bending moment at point C. Okay, so let's go for Q&A. Sorry, for checking on the presence. I stop recording at this time and then try to